So in this video we're going to look at a couple types of symmetry you might see with polynomials when you graph them. And we're going to specifically talk about something called even functions and odd functions. So just like numbers could be even or odd, a polynomial might be even or odd. So take a look at these graphs and see what you notice. Just kind of pause and take a look. What are some things you notice about these two even graphs, first of all? And then what are some things you notice about these odd graphs? Okay, so you probably noticed, especially on the even ones, that they're symmetric about the y-axis, meaning if I were to pick it up and flip it over the y-axis, I'd get the same graph. Same thing here with this parabola. With the odd ones, it's a little odd, but you may notice it's kind of a rotation of itself. With odd functions, what happens is, if you were to take the graph and rotate it 180 degrees around the origin, you would get the same graph. We call that like rotational symmetry, where this is like reflection symmetry. Okay. And then here's a couple examples of their equations, not the ones that I just had, but some equations of some even functions are x squared, x to the 10th plus 5, and 7x to the 4th minus 6. Anything you notice about each of those equations that might make it even? Or, for example, the odd functions could be x cubed, x to the 17th, plus 5x cubed, 7x to the 5th minus 6x. Again, anything you notice there? Okay, so here's something you may have noticed. Each of these has even exponents. Each of these has odd exponents. So that doesn't always happen, but that's often where it comes from, is functions that have even powers are often even, functions that have odd powers are often odd. That's not always true, but so even functions usually have an even degree, meaning the highest exponent's usually even. And they are symmetric about the y-axis, so you can flip it over the y-axis. Odd functions usually have an odd degree, not always, and they are symmetric about the origin. Meaning you could rotate it 180 degrees around the origin and get the same graph. These are a few examples, but there are more. So they don't always have an even degree or an odd degree. For example, the square root of x. We've talked about its graph a little bit. Its graph just makes a v. Well, that was a bad v, but you get the idea. This one is symmetric about the y-axis, making it an even function. An odd function would be the sine wave, which we haven't talked about a whole lot, but it looks kind of like this. And it continues forever in both directions, but if you were to rotate it 180, this is the function sine of x. So they don't always have an even or odd degree, but they are always, even functions are always symmetric about the y-axis. Odd functions is just the name we give to functions that are symmetric about the origin. So let's look at a few examples. Is this one even or odd? This looks like a book page to me. This one's even because it's symmetric about the y-axis. That one's even. Is this one even or odd? This one's odd because if you were to rotate it 180 degrees around the origin, you'd get the same graph, so that one is odd. All right, so what about these? Like, let's take a look at this one. Is this one even or odd? It's tempting to say even because I could reflect it vertically and get the same graph, but that's not the y-axis. Like this right here is not the y-axis. This is. If I were to reflect this across the y-axis, it would look something like this. That's not the same graph. And if I were to rotate it, it would look something like this. And that's also not the same graph. Same thing for both of these. If we were to reflect it across the y-axis, or if we were to rotate it 180 degrees, we would not get the same graph. So it is actually possible to have a function that is neither even nor odd. All of these are examples of that. They're not symmetric about the y-axis, and they're not symmetric about the origin, so it's a neither. In fact, most graphs are actually neither. It takes a special graph to be even or odd. Just as a side note, this is true of numbers as well. Only whole numbers could be even or odd. If you ever have like decimals or fractions, those are neither even nor odd. Okay, here's an example of a multiple choice question you might see with this kind of thing. Which of these is an even function? So probably only one. The answer is going to be this one, because it's the only one where it has y-axis symmetry. You could flip it across the y-axis and get the same graph. All of these are symmetrical, but not across the y-axis, because this one would look like this if you flipped it over the y-axis. This one would look like this if you flipped it over the y-axis. So again, these are all symmetrical, but only this one's an even function. Okay, another kind of example you might see is like, finish the graph below if it's an even function. For example, if I gave you this, what would the rest of the graph look like if it were even? Well, if it's even, it should be the same thing on either side of the y-axis. So it would look like this and make like a W-looking thing. There are quite a few letters that have this symmetry. Like, we could make like an A or something. Or we could make like an M or an N if it were slanted. Gotta make sure it's a function. No, an N wouldn't work, sorry. An N would have symmetry about the origin, so an N could be an odd function. Here's another example. If I wanted to finish the graph, if it's an odd function, like let's say it looks like this. If I were to rotate that 180, it would be like down and up. So that would be an example of finishing the graph if it's an odd function. Okay, so you can always just look at the graph and see if it's even or odd, but you can also test algebraically to see if a function is even or odd. And here's how that works. The test is plug in negative x instead of x to your function. If you get out what you started with, it's an even function. If you get out what you started with but completely negative, it's an odd function. And here's why. Let's think about the graph of x squared. This is an even function because it's symmetric about the y-axis. Notice that if I plug in a value like 2, I get out 4. And if I plug in negative 2, I get out the same thing, positive 4. So whether I plug in a positive or a negative, I get out the same value because it's got this symmetry. That's why with even functions, if you plug in a negative x, you should just get out the same thing. And you'll see what I mean here in a second. With odd functions, if you plug in a negative value, like let's think about x cubed. X cubed looks like this. It's an odd function. If I were to plug in a 2, I would get out 8. And if I were to plug in negative 2, I would get out negative 8. Notice, if I plug in the negative version, I get out the negative thing. So here with odd functions, if you basically put a negative in there, it's going to turn the whole thing negative. That's basically because they're in like opposite quadrants. Okay, so here's some examples of that. Are these functions even, odd, or neither? Again, you could just graph them if you want to do that on your calculator, Desmos, or by hand. Or I could test algebraically by plugging in a negative x. So instead of x squared, what if I did negative x squared? If I simplify this and get back to just x squared, then it's even. If I simplify this and get negative x squared, then it's odd. Think of this as like a -1 here. What is -1 squared? -1 times -1 is just 1. Or think of it as -x times -x would give you positive x squared. Either way, the negative goes away when you simplify that, and you get just plain old x squared, which proves that it's even. We got back to what we started with. And we kind of expected that, right? I mean, it has an even degree, so odds are it's probably even. It's definitely not odd. It could have been an either, though. Let's try this one. Again, we know it's odd already, and it probably is odd because of the degree, but if I were to plug in a -x, will I get out -x cubed? If I do -x 3 times, so like -x times -x times -x, notice that it is still negative. This simplifies to just plain old negative x cubed. Since I got the complete negative version of what I started with, that makes this odd. Let me show you a couple other quick examples. Actually, we'll do that in the next video.